Okay, so remember what we said here. If we've got some blue function and we want to do a quick approximation of the function, then we can do what's called a linearization, right? So we're just gonna approximate the blue curve with the green line that's tangent to that curve. And it doesn't always have to be blue and green, by the way. That's just the way it is. So you can see on here that that's only going to make sense if we're speaking locally, right? So in the vicinity of that point. When you start to get too far away from the point, obviously the linear approximation is going to diverge from the function. It's no good anymore. But when it works, it's really a quick and easy way to get an approximation of a function. And so what we said then, and I want to just draw your attention to this because it's so easy to remember this relationship, right? All we said was that if we go out some distance, delta x or dx, if we want to call it that, the actual change in the function I would just get by the value of the function here minus the value of the function there, right? But we can approximate the change in the function by how much the line changes, right? Which we could call dy. Well, think what that means. If this is the slope of the line, right, and that's determined by the point of tangency, right? So the slope of the line, as it always has with our derivative stuff, corresponds to the slope of the function at the point of tangency, right? So that's what we call m. Well, m is just equal to the slope of the tangent line, or dy dx is just equal to f prime of c then, right? And so dy is always just going to be the slope of the function at c times dx, right? And so that's the relationship we get, which makes total sense because we don't even have to think about that in terms of the picture. That's just what we call the differential form of a derivative, right? If we start with the relationship dy dx, which is one way to say a derivative, is just equal to f prime of x, then to put that derivative in differential form, all you do is multiply both sides by dx. And so the differential form of the derivative is dy equals f prime of x dx. We don't even need the graph to demonstrate that. That's just a different way of writing calculus notation that we can completely separate from this picture if we want to. So for example, if we've got the function, let's say y equals tangent x, then what's the differential form of that derivative? Dy equals secant squared. So it's the regular formula, but then at the end I'm just going to tack on a dx. We can even make it more complex. It could be a chain rule thing. So we can do something like this too. What if we've got y equals, I don't know, let's say we've got secant of 3x squared. So what's dy?
Negative secant squared, 3x squared.
Secant tangent. So we'd have.
Is it cosecant that goes to like negative cosecant
Yeah.
squared? Okay.
Cosecant goes to negative cosecant cotangent.
Oh.
Cotangent goes to negative cosecant squared.
Okay.
Times what?
6x.
6x.
Yes.
And then I got to tack on a dx, right? And among other things, that's going to become very useful to us. And I even did an example of this last time we talked, when we solve differential equations, right? Which is we're going to start doing next week, right? We're going to move on to integral calculus and kind of reverse this whole process, okay? So how is this useful to us in other ways? So this, I thought we did.
This one's 21. This one's 30.
I wonder if that's attached.
There was more thought than that. You just.
No, like in my head it made sense. Like,
Huh? Why am I gonna do that?
the obviously there was no reason to take